Here we want to divide using long division, and then we're going to look at what we can learn from the quotient in that long division. As we look at our polynomial p of x, so 2x cubed minus 14x plus 12, notice that this polynomial is degree 3, but as we look at the terms, it's missing an x squared term. It goes straight from x cubed to x without having an x squared term. So when we set up our long division, we need to account for where the x squared would have been. So we're going to start with our x plus 3 out in front. Underneath we'll have our 2x cubed, and then to show that we don't have an x squared term, I'm going to do a plus 0x squared as what we call a placeholder. We have our minus 14x and our plus 12. Remember, our process for long division is to divide, multiply, subtract, and then bring down. So I'm going to begin with the leading terms. 2x cubed divided by x gives us 2x squared. After we divide, we multiply. So 2x squared times x, and then 2x squared times 3. We're subtracting now. 2x cubed minus 2x cubed, those terms cancel. And 0 minus 6 gives us a negative 6x squared. Bring down the next term, start the process again. So now we're going to take our negative 6x squared on the inside and divide by x on the outside. So negative 6x squared divided by x gives us a negative 6x. Then we multiply. Negative 6x times x is a negative 6x squared minus 18x. Be really careful with your signs on this subtraction step here. So negative 6 minus a negative 6, those terms cancel. When you have a negative 14x and you subtract a negative 18x, it's like adding 18x. So negative 14x plus 18x gives us a positive 4x. And then one last time, bring down our plus 12. So one more division, 4x divided by x gives us a positive 4. 4 times x is 4x, and 4 times 3 is 12. So as we subtract, 4x minus 4x cancels, and 12 minus 12 also cancels, so we have a remainder of 0. So a remainder of 0 tells us a lot of key information. So the factor theorem says having a remainder of 0 tells us that we've really found a factor of the original polynomial. So x plus 3 is a factor of p of x. If we know a factor, we know a 0, and a 0 tells us about horizontal intercept. So here's some things that we can say at this point. So our original polynomial p of x was 2x cubed minus 14x plus 12. By finding that we have a remainder of 0, what we found is that you can factor p of x and write it as x plus 3, our original divisor, the thing doing the dividing, times our quotient, 2x squared minus 6x plus 4. You can check if you were to multiply those out, you get back your original polynomial p of x. Well, now that we've been able to factor out that x plus 3, we can continue on with what we know from earlier sections and factor this trinomial that was left behind. They all have a common factor of 2, so we call that a GCF. So I'm going to go ahead and factor out that 2, which leaves an x squared minus 3x plus 2. And then we can factor again, thinking about two numbers that multiply to 2, positive 2, but add to negative 3, and write this as x minus 2 times x minus 1. So if we put all that together, we found that our original polynomial p of x can be factored as 2 times x plus 3 times x minus 2 times x minus 1. So the reason that we're able to do this factoring is that when we did our long division, we had a remainder of 0. So that told us that our initial divisor, x plus 3, was a factor of our original polynomial, and then we could factor our quotient to find the remaining factors. As we've seen in previous sections, each one of these factors then tells us about a 0. So if we were to set each of these factors equal to 0 and solve for x, we see that x equals negative 3 x equals positive 2, or x equals 1. These are what we call the zeros of our polynomial. We could also then think of those as our horizontal intercepts. So the point -3, 0, the point 2, 0, and the point 1, 0 are the three horizontal intercepts for this particular polynomial function. So the long division allowed us to factor. From those factors, we can find our zeros, and from our zeros, our horizontal intercepts.